Okay, so let's look into differentiation. Yes, it's my font here. This one is okay. So I think that is great. So let's start with the definition of a derivative. So we define a derivative as a measure of the rate of change. So a derivative is a measure change the rate of change. Right, so that's what we have. Just a second. Just a second. Right, so that's what we have there. So a derivative of a function is just a measure of the are as follows: f prime of x. We can have differentiating with respect to x, so that's d sub x. And we can have differentiating a function called y with respect to x, and all these other notations that mathematicians are using. All right, so that's what we have there. Then we want to look into the investigation now. We want to look into the investigation of the first principle. All right, of the first principle. Just a second. I just want to share these. So to quickly share these. Let's copy. Right, so let's try to then continue. Okay, so we want to investigate the rate of change formula. Okay, so just allow me to add my Cartesian plane. Let us see if I can add there. Okay, I think I'll just use my hand. Let's say we have our x-axis. Let's say we have our y-axis. Okay. So now let's say we have point x here. Then we have another point there which is called x plus h. So h is nothing but the step size. And I'll just have a curve. I'll just have a curve like this. And I'll have these 2 points here. And I'll have these 2 points. So I'll call this one A and call that one B. So we all know that this point here will just be x and its corresponding y value, and this one will be x plus h and its corresponding y value. Right, so if I was to bring in what we call a tangent line, right, at any point x, right, at any point x there, so we know that a tangent line will just interact with the curve at one point, right? At one point. So if I was to bring in the tangent line there at any point x, I will then try to work out the gradient. So let me just add the tangent line there. Fortunately, I don't have the ruler here, so I'll just do something like this. But I wanted this to interact with the function only at one point. Right, so let's say this is the point where the intersection is occurring. And I'll then bring in another line, right, which is parallel to that tangent line. All right, so I'm just going to bring another line like that. Okay, so it should be a straight line. Okay, and a ruler. So let's say we have that. So looking at that, we can then say that the gradient of the let me say the gradient of the tangent line of the secant line. All right. Okay, so that's what we have there. So what we are trying to say is that these two lines are parallel, so they should have the same. So from there, we can then say the gradient, which is the rate of change, the gradient of the tangent line is actually y2 minus y1 over x2 minus x1. Okay, so that's what we have there. That's what we have. Then we are going to try and substitute this. So this will then be f of x plus h minus f of x. And this will all be over your x2 minus your x1. So that's what we have. That's what we have there. So let's just try to then work out the denominator. So this will then be f of x plus h minus f of x, then all over h. All right. Okay, so the slope of the tangent line can be expressed now as this guy, since this is a measure of the rate of change. So we can have something like that. And then now this will depend on the step size, right? This will depend on the step size. So what we are going to do, we are then going to say this will look into the behavior of these step size there. So we then bring in the concepts of limits to say when h approaches 0. So the limit, the behavior of the function or of the curve when h tends to be 0 of this rate of change. So the gradient will depend on the behavior of the curve when h tends to 0. So we now have this f prime of x, which is equals to the limit as h tends to 0 of the quotient f at x plus h minus f at x all over h. And this is what we call the first principle. This is what we call the first principle. Okay, right. So now we have investigated the first principle. Okay, so add a page there. So that we can continue. So we now have the first principle. We now have the first principle. Let me just put this on do not disturb. Right, so we now have the first principle. Then we can now try to look into its application. We can now look into its application. I want to add multiple pages. Page 3, page 4, page 5, page 6, 7, 8, 9, 10. Right, I think that will be enough. Okay, so we have our first principle. So we're going to then look into the application of this first. Right, let's hope when I'm in the focus mode, things are going to be well. Okay, there we go. I'm just choose another color here and have the red. Let me work out this and show steps only. Just a second. Yeah, in most cases I use the one note, because this one tends to give me a problem. All right, fine. So let's look into our first example. Example 1. Say that we want to find the f prime of x if f of x is equals to x. Okay, so let's start with that one. And let's see how we are going to work out the first derivative. Right, so we're just going to have our solution. We write the first principle, so we have our f prime of x, which is equals to as h tends to 0 of f of x plus h minus f of x all over h. So that's what we have. Then from there, we have to then evaluate some of these parameters, like this portion here. Let me just select the pen there. Okay, so we end this portion, then we can just plug in our evaluations into our formula, like for f at x plus h. So we know that f at x is equals to x at x plus substitute this new value of x there, which is our input on that function f of x. So if we do that, this will then putting this input value into my function there, right? Into my function. So it becomes x plus h. It becomes x plus h. I have this evaluation, which is f of x. So f of x is given to us. F of x is given to us as x, as variable x. So we don't need to crack our skull on that one. We don't need to crack our skull on that. Okay, so that's what we have. I hope everything is still clear. So we'll then take everything and substitute it into our formula. All right, the first principle. So I'm going to have the limit as h tends to 0. What is my f at x plus h is nothing but x plus h, then minus f of x. F of x is nothing but x, right? So this will be all over. Let me just work out that. Trying to work out this part. I think I can just do this. Okay, so that I don't go back and forth to enable the pen there. Okay, so that's what we have, and let's see if we'll be able to work out this. So this whole thing is all over h. Okay, so we can see that you're going to have cancellation, and that's the good and interesting part for over h. Okay, so that's what we have. That's what we have. Then let's then try to simplify further. So if we simplify further, this will imply that our first derivative for this function of x will be the constant 1, because it's nothing but 1. Okay, so that's what we have there. Then we'll then try to take the limit there. Of limits, we know that the limit of a constant is nothing but a constant. F prime of x will just be the constant itself. So what do we have now? It's f prime of x is equals to what? It's equals to 1. That's what we noticed when we applied our first principle there. That's what we noticed when we applied our first principle. All right, so that's what we have there. And then we are going to take our second example. We're going to take our second example and then see how things will transpire there. Okay, so let's just take a heavy one. Let's just take a heavy one. Let's just take a heavy one. Okay, so this will be the second example. F prime of x, if f of x is equals to x squared minus 3x. Okay, so take a look at that and then try to think about it. Try to think about it and let's see if things are going to be simple again. Right, so we are looking for the risk principle, which you know by first principle is nothing but as h tends to of the quotient of f of x plus h minus f of x, then all over h. That's what we have there. That's what we have there. Then we are going to try and do the very same thing that we did with the previous example. So we'll try to evaluate all these parameters, your f of x plus h. So our f of x plus h, we can see that our f of x plus h implies that we just need to substitute our x there with the new input value, which is the x plus h. Okay, so we're going to do that. So whenever I see x, I'm going to plug in this new value of x, because I have f of x, which is given to me, but I'm looking for f at x plus x squared. So what is my new value of x? Is x plus h. Then I will need to square that. Then minus 3 of x. What is x? My new value of x is x plus h. Okay, so I have that. Then from there, I'll then try to work out these brackets. So we have our x plus negative 3 multiplied by positive variable of x. This becomes negative 3x. Then negative 3 multiplied by the positive of our step side. So that's what we have there. That's what we have. Then we'll then try to work out the brackets. So working multiplied by x, which is x squared, then x multiplied by this h, this will be plus xh, then h multiplied by x, this will be plus hx, which is the same as xh, because multiplication for 1 h multiplied by h, this will just be so far. This is what we have so far. I just want to write down the x squared minus 3x on the paper there, because I will need it down there. I hate scrolling up and down, so I just want to put the guys is x squared minus 3x. So I'll just put it there just for in case, just for in case. So let's try to then work out the simplification there. Do we have like terms? Do we have like terms there? So we notice that we have these two. We can add, right? Of which we can add up the xh plus xh, x squared, add by 2xh, then add by h squared, then minus your 3x, then remove your 3h. So this is what we now have. This is now what we have. We have x squared, add by 2xh, add by h squared, then remove your 3x and remove your 3h. All right. So now we have this. We are happy now. F of x, we have it there. So we're just going to take everything now and substitute into our formula. So our first derivative, or the rate of change, or the slope of the tangent line, will be the limit as h tends to 0 of what? So I'm just going to have the x squared plus 2xh plus h squared, remove your 3x, remove your 3h, then minus f of x. F of x, remember, is x squared, remove your 3x like that. Then this whole thing is over h. Right, this whole thing is over h. So that's what we have. Now we have to play it safe. We need to play it safe now. We have to work out the brackets first, and we should see cancellation. We should see the cancellation there. So I'll say this is equals to the limit as h tends to 0, which is the behavior of the function. So I have x squared add by 2xh, then add by h squared, remove your 3x, remove your 3h, then I can then multiply the bracket out, it becomes minus x squared, then add by 3x, then this over h. So I can work out and will undo what is going to remain. So we are going to remain with the limit as h tends to 0 of 2xh add by then all over, let me just fix my, where is it? So this will be all over h. Then when we are there, we can apply two approaches there to factor out the common factor here, everything by h there, because we know that if we have a plus b over c, we are allowed to split this to a over c plus b over c. So we can apply that. So this will be f prime of x equals to the limit as h tends to 0, right? As h tends to 0 of, we're going to divide each term there. So 2xh divided by h, 2xh divided by h, then plus h squared divided by h, then minus 3h divided by h. So that's what we have there. That's what we have. Okay, so from there we can now simplify. We can now simplify further. So this will then be equals to, the limit as h tends to 0 of, if we divide 2xh by h, the h are going to undo each other there. The h's are going to undo each other. So we'll remain with 2x. Then let's move to the second term. We have h squared over h. So if we work out that, this should be, we have two variables of h on top, and we have one variable of h below, so we can cancel out one there. Then we remain with h. Then for the third term, we have minus 3h over h. So the h and h are going to undo each other. Then we are left with minus 3. Okay, so that's what we have there. That's what we have as our simplification. Then now we're just going to take the limits, going to apply the limit there, check the behavior of the evaluating the limits. We have direct substitution. We have limits by factorization. We have limits by rationalization, right? So for this one here, we can just direct substitute the value of h, right? We can direct substitute the value of h. So this will imply that we'll end up with 2x. And remember, I'm evaluating the limit, so I'm going to drop the limit there, right? So I'm going to have my 2x plus, what is h? H tends to 0. So if I see h, I plug in the 0 there. Then minus 3. All right. Otherwise, one can then say I'm applying the laws of limits, right? The properties of limits. Then you can take the limit for each and every term there. You can take the limit for each and every term. So this will then be our final answer. X was derivative of this f of x is nothing but 2x minus 3. Okay, so that's the derivative of our guy there. That's the derivative of our guy there. Okay, right. So this is how we apply the first principle. This is how we apply the first principle. And this can get into an interesting part whereby you want to evaluate the first derivative of a rational function, or the first derivative of a radical function, and all these other functions. All right, so it can get interesting there, right? So we will then jump into the rules of differentiation. We'll then jump into the rules of differentiation. The rules of differentiation. All right, so before we tackle the rules, we'll then try to more like look into other functions as to how we can evaluate the derivative of these other functions. Okay, and that will then take us to the rules themselves. All right. Okay, so the first rule we say if then the derivative of f of x will just be 0, right? So we're just going to try and prove that, to say if f of x is a constant, then f prime of x, which is the rate of change or the derivative of f, is equals to 0. So I'm just going to try and prove that case there. So I'm just going to write the proof here. I'll say proof. So I'm going to use, what is the first principle? The f is nothing but, okay, the instantaneous rate of change of this function is nothing but the limit, the behavior of the function of x all over h. So that's what we have there. That's what we have. And we want to look into that. We want to look into that. Okay, let's get into it. So now the f constant function, right? This is a constant function. This is like you have something of x to the power of 0, all right? Because we know about x to substitute our input value. So let's look into that and let's see how things are going to work out there. So I'll then have my c, then I will substitute this new input value in this function, right? Because cx to the power of 0 is the same as c times 1, because x to the power of 0 is nothing but 1, all right? So I just multiplying that constant by 1, and nothing is going to happen. This whole thing will just be that constant, right? The y value at at x plus h will just be that constant, because this guy is a constant function. This guy is a constant function. So this guy is something like this. It's a constant function. So I have my y here, I have my x here. So this guy is a constant function. So this guy can be something like this. This guy can be something like this, right? Where you have now your f of x equals to a constant, and this constant can be positive and this constant can be negative. All right, this constant can be positive or the constant can be negative. So I can have another guy here if the constant is negative. Can have f of x equals to that negative constant. Okay, so that's what we have there. That's what we have. Okay, so I'm just putting the drawing there so that we can see what is going on. Okay, x plus h, which is information, then we'll plug it into our first principle here. Then we'll then see the derivative of the constant function. Okay, so let's have a look into that. So we have f prime of x, which is going to be the limit as h tends to 0, as h tends to 0 of f of x plus h, which we notice that is nothing but the constant function itself, then minus f of x, which is minus c, then all over h there. Then we can now work out the simplification there. So this will then imply that the f prime of x is nothing but the limit is the same as 2 minus 2, which is just a 0, right? Which is just a 0. Then a 0 over any quantity, the answer will just be at the origin. This will be nothing but a 0. And now we have proved that if we have a constant function and we differentiate that constant function, the derivative of that constant function becomes nothing but 0. Okay, so I hope that is clear. I hope that is clear, and it's a very nice and short proof. Okay, so not sure if you guys have any other questions. Okay, if there are no questions, I think we can look into the sum, the derivative of a sum of two functions, the sum rule. So our number 2, the sum rule of differentiation. So we are saying if f of x is equals to g of x plus h of x, then which is the derivative of f, the derivative of a sum of two functions is nothing but the sum of the derivatives. So we have to prove that. We have to prove that. And let's see how this will look like. So I'm going to write the proof here. Then I'm going to try and write the first principle. As you will see that mainly on the proofs, we go for the first principle, right? We'll just go for the first principle. So what is our first principle? Should be equals to the limit as h tends to 0, then all over h. So that's what we have there. Then we're going to try and work out these quantities. Okay, let's start with the first quantity, which is the f of x that is given to us. We need to substitute the input value x plus h wherever we see x, right? So I'm going to do that. We have g of x. So remember, x function f is x plus h. So wherever we see the x, we can plug in our x plus h. Then add by what? Add by h of x. And remember, x is what? X plus h. So this will then be h into x plus h. But now I'm going to have a problem there. So allow me to change this to k, because looking at what we have there will more like temper with our initial age in the first principle. So allow me to then make this one to be function k, right? Sorry about that. Yeah, so we have that sum of those two functions, g of x. Okay, so we're just trying to prove that the derivative of a sum is nothing but the sum of the derivatives. So let's move on. So I'll then plug in everything into my first principle. So I have my f prime of x will be the limit as h tends to 0 of f of x plus h, which is g of x plus h, then minus into f of x. F of x is g of x. This will then be all over substitution. So this will end up being the limit. I'm just going to try and work out the bracket there. G of x plus h, each and every function there, which have my, and this will be all over h. So that's what we have there. That's what we have. So let's try to unpack this in a nice way. So this will be the limit as h tends to 0 of the g, then I'll say plus k of x plus h coupled. Right, so this will be all over h. This will just be all over h. Remember, this is still our f prime of x. So that's what we have. So I'm going to try again to then try to couple them again. Okay, so I'm going to just put the square brackets here on the previous guy just to save time. So what I'm going to do is I'm going to apply this limit property to say that the limit as x tends to a as the limit as h tends to a of the of x. So this is what I'm going to apply. This is the property of the sum, the limit of the sum. Right? I'm going to apply that into my problem. F prime of x equals to the limit as h tends to 0 of, I'm going to split that, so I'm going to have the g of x plus, and this whole thing will be h tends to 0 of x all over h. I'm just applying the sum rule of the limits there, right? It's highlighted in red, the one that is highlighted in red. So it allows me to distribute the limit throughout the functions there. So we are saying that the limit of the sum is actually the sum of the limits. Okay, so let's try to move on. We are almost there. So now what do we notice? We notice that the first derivative of this function f, or derivative of f, or the rate of change, or the instantaneous rate of change of f is nothing but, we recognize this guy, right? This guy is in the form of a first principle applied on a function g. So this will just be our g prime of x. Then plus we recognize this second guy as another first principle applied on a function k prime of x. Okay, so that's what we have. It's equals to g of x plus k and f prime of x is equals to the derivative of g and by the derivative of h. So that's what we have. And we have proved that using our first principle. All right, using our first principle. Okay. So in the same way, the first principle, you'll see that if y is equals to f of x minus g, which will be notation. this your g prime of x. Okay, so we can still prove this in the very same way that we proved the previous guy there, the sum rule. So we can have the difference rule and we prove it in the same way, right? So this is the difference rule. And this is very important because you can apply it in the field of engineering, in the field of IT, the field of applied mathematics, and in the field of calculus itself. Okay, so it's very important to know this multiple function rule. So the constant multiple function rule states that if f of x is equals to a constant multiplied by another function, the solve multiplied by the derivative of the function. Okay, so we are going to prove that. We are going to prove that. We have to prove that. So I left with two rules which we need to cover for today. Right, so let's look into it. So we are going to have our proof here. Then say proof f in the first principle. So in most cases, we normally say let f of x be equals to c g of x. There, so we then bring in the proof there. Okay, so I'm just saving time on my side. The limit as h tends to 0, then all over. I'm just going to plug in my new function f here. So whenever I see x into the function f, I'll plug in the new value, which is x plus h. Okay, so let's do that. So if I do that, you guys will agree with me that will end up with c new value of x into my original function, then minus f of x. Remember, f of x is just c g of x. So I have that. Then this whole thing is over h. This whole thing is over. And my connection is weak. Okay, so our next step to try and factor out the constant there. To try and factor the constant. So this will be, so I'll factor out the constant. So I'm going to have c into g of x, right, all over h. So that's what we have as our, as per our factorization there. Right, so then from here I can then push out the constant and take the limit of the function of h minus the g of x all over h. Okay, we are almost there. So what do we notice? We notice that the constant will be multiplied by this guy here, and this guy is similar to our first principle applied on a function g. So this will just be c g plus the derivative for function f. So I then multiplied by g and itself multiplied by the derivative of g. Okay, so we have proved that part. We have proved that part, and that's what we wanted to prove. Okay, so the last proof for the day is the power rule for all polynomial functions or all power functions. Okay, let me just remove this. not sure as to what did I press now. Not sure as to what did I press. Okay, just a second. Okay, then it's back. Okay, so let's look into the power rule, which is our last part for the day. Let's look into the power rule. Okay, so this should be your number rule of differentiation. The power rule states that if f of x is equals to any function of this form, x to the power of n, then f prime of x is equals to nx to the power of n minus 1. So that's the power rule. That's the power rule, and we want to then prove that. Okay, so then bring in our first principle. We know that the first principle is useful when it comes to evaluating the introduction to calculus. The first principle is going to fail us somewhere, so we'll need to look into other rules which are well known. Right, so we have this first principle: the limit as h tends to 0 of f of x plus h minus f of x, then all over h. So that's what we have. Okay, so we are going to do the very same thing. We're going to do the same thing and look for f at x plus h. Okay, so let's look into that. 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 Okay, so let's have fun. Let's have fun. So let's start. So our x, remember, is given to us as x to the power of n. So that's what we have. Then let's try to then work it out. So this should be f minus x to the power of n all over h. So that's what we have there. Then now we have a problem. We have a problem here because we have to know the evaluation of this guy. And to evaluate this, we need to have a background of the binomial theorem. Okay, we have to have a background of the binomial theorem there, the expansion of the binomial theorem. All right, so the expansion states that This guy is nothing but x to the power of n plus n x to the power of n minus 1 h, then plus n into n minus 1 all over 2 factorial, then h squared, then plus blah 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 up until the end, where you'll have the h to the power of n itself. Okay, so that's what we have. That's what we have when we look into the binomial theorem to expand that guy, right? To expand that guy. That's what we'll end up having there. And it's a very nice expansion, like a theorem. It's very nice. It's very nice. It's within your abstract algebra. It's within your abstract algebra. Okay, so now let's get back to business. So this will be this. Uh, then let's try to work out what we have there. The expansion, we have the expansion is just x to the n plus nx to the n minus 1 of h plus da 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 plus h to the power of n, then minus x to the n, right? So I'm not writing those other terms because I don't really need them. So I'm going to have the h there. Okay, h tends to 0. So we normally see that this one and this one are going to undo each other. So I'll be left with n x to the power of n minus 1 times h plus n into n minus 1 h squared blah blah the power of n, right? The h to the power of n there. So that's what we'll end up having. That's what we'll end up having. All right. So we are here, and this whole thing, remember, is all over what? Is all over h. So if we work out our math, now we'll end up with n x to the power of n minus 1. This h is out, then plus the n into n minus 1 all over 2 factorial of h, because I'm dividing there, then plus the last one will just be your h to the power of n minus 1 when I divide by that guy. Okay, so taking the limits, so this if you plug in 0, 0, this will then imply that our to the power of n, then the derivative of that function will just 1. And we just proved that. We just proved that part there. Okay, so that's what I wanted to cover for today. Then next time when we meet, we'll look into the derivative of the product and the derivative of the quotient, right? When we have two rational functions, how will we work out that? Okay, thank you so much for availing yourselves. I'll see you guys when I see you.